Okay, so what did we do last time? Let me remind you. Last time we basically looked at a very, very simple example, and we discovered supersymmetry in that example. The example that we had two scalar fields and two Weyl fermions, two component fermions. And we saw that supersymmetry is an extension of space-time supersymmetry, of space-time symmetry. And we saw that the vacuum energy is 0 if supersymmetry is exact. We saw that we have same number of fermion and boson degrees of freedom. And actually, except for the fact that we didn't have the vector field in the story, so we didn't say anything about vector fields, except for that fact, we really have everything we need. So in principle, we could just keep everything the way we did it, not introducing any new language, and just go on with that, because we really have all the elements that we need. And the one interesting thing, or one of the interesting things that we got out of this last time, is this other example of an interacting theory, where we had these three scalar fields and the accompanying fermions, and we added a bunch of interactions, and we said that the delta m squared of the scalar is only logarithmically divergent. And we said that that's the thing that makes supersymmetry useful for solving the naturalness problem in the standard model. This thing, of course, should remind you of the standard model. That's the reason for the notation here. So this guy is like the Higgs, and these guys are like the left and right tops or stop plus tops. So if you think about the standard model below the scale of electroweak symmetry breaking, there's just a U1 symmetry, and that's the reason for these plus and minus subscripts. You can think of this guy as a field of charge plus, this guy is a field of charge minus, and all the interactions that we wrote down respect that symmetry. So in principle, we could gauge that symmetry, and we get something that's very similar to what we have in the standard model, and gives us a cancellation between the tops and the stops, and no quadratic divergence in the Higgs mass. So in principle, things are very simple. And I told you last time that we want to keep notation very, very simple so that the indices don't obscure the physics. But today we're going to bring the indices back on. And we want to introduce a little more formalism. So what we want to do today is add more formalism. So basically I'm going to introduce a little bit of spinor notation. We're going to introduce dotted and undotted indices. And we're going to introduce superspace. And the reason we want to do that is really to simplify our lives. We're going to have lots of spinor products come in, and we want to keep the clutter at a minimum, and we also want to be able to write down Lagrangians in a way that's manifestly supersymmetric. I mean, last time we wrote some Lagrangian, and it was a simple Lagrangian, but you had to work very hard to show that it was indeed supersymmetric. But now we're going to have some prescription for writing down theories such that we know automatically that the theory is supersymmetric. So we don't need to work very hard. So it's just like with Lorentz. I mean, you're not going to write down a Lagrangian and write down separately dt phi squared minus dx phi squared and so on and so forth. You write something that's manifestly Lorentz invariant. So that's what we're going to do. And it's 9 o'clock in the morning, and it's air conditioning. It's not 2 o'clock, and so there's no problem. Okay, so the first thing we want to start with is making the supersymmetry algebra, making the SUSY transformations a little more simple. So last time, going back to our very first example, we had this, we saw that, so we're going to talk about auxiliary fields now. And you remember that last time we said that if we take the anti-commutator of two Lorentz generators, we get something that's proportional to translations. But this was something that only happened when we imposed the equations of motion on the fields. So this is something that happened after we used the equations of motion. So now we want to write down a version of the theory where we're not going to need to impose the equations of motion. Everything is going to hold, and this algebra is going to, this anti-commutator will give us translations even off-shell. So in order to do that, we introduce auxiliary fields. And the basic little module that we had before had a scalar field phi plus, for example, a fermion, the psi plus, and now we're going to add an f plus to the story. So this guy is spin 0 and has dimension 1. This guy is spin 1/2. And the field has dimension 3/2, and this guy is a Lorentz scalar, and it has dimension 2. And now I want to write down the transformations, and maybe let me write them over here, and I can keep them here for some time. So now this is going to be, here I wrote down the pluses, but I can really omit the subscript because it's going to hold for any supermultiplet like this. So these are the transformations. There's delta xi phi plus. That's going to be equal to square root of 2 psi t epsilon psi. This is just like we had before, no change. Then we have delta xi of psi, which is square root of 2 I sigma mu epsilon psi star d mu phi. Again, the same thing that we had before, but now we add another thing, which is square root of 2 xi f. So this is the new part in the story. And then we have to include the transformation on f, which is minus square root of 2 I psi t sigma bar mu d mu psi. So the Lagrangian that we want to write down in this case is, first of all, the same thing that we had before. So now let me write it for both phi plus and phi minus. So this is d mu phi plus, d mu phi plus, plus psi plus dagger I sigma bar mu d mu psi plus f plus squared, and the same thing with plus replaced by minus. And then we have the mass term m psi plus t epsilon psi minus plus the complex conjugate, and finally M phi plus F minus plus M phi minus F plus. So these are the transformations, and these are the Lagrangian. And there are a few things to note about this. First of all, you can take now the commutator of two supersymmetry transformations, like we started saying over here. I can take now delta xi, delta eta, this commutator, acting on any of the fields, and I'm going to find something that's proportional to d mu of the field without using the equations of motion. So with this auxiliary field that we introduced, one for the plus and one for the minus guys, the algebra closes off shell. The second thing that you want to notice is that indeed this F is just an auxiliary field. What does that mean? It means it's not dynamical. So F is auxiliary, it's not dynamical, and we didn't write any kinetic term for F. You see there's no kinetic term for F here. So we can solve the F equation of motion very simply. For example, for F plus, if I impose the equation for F plus, then it tells me that F plus star is equal F plus star plus M phi minus equals 0. And I can go back and substitute that into the Lagrangian, and I will recover the same Lagrangian that I had before. Another thing that we want to notice is that when we look at the SUSY transformation of the auxiliary field, we get something that's a total derivative. It's just a total derivative of the field, and there's really nothing else that we can write down, because this guy is the highest dimension field in the multiplet. Okay, this guy has dimension 2, and so this is the only thing that we can write down over here. And that's going to be something that will have significant consequences, as we'll see. Okay. So that gives us a simple way to write the Lagrangian. But now comes the real utility of this. So basically, now that we introduce this auxiliary field, we can come up with a completely general recipe for constructing supersymmetric theories. So now we know how to write down a general SUSY Lagrangian that includes just chiral supermultiplets. So suppose we have a bunch of chiral supermultiplets, phi I, psi I, fi. There's a number of this. Then this is the recipe. You should take some analytic function of the phi i's. We're going to call that function w. So w is a function of the phi i's. What does it mean that it's analytic? It means that no phi I stars appear. Okay, so it's just a function of the phi's. This function is called the superpotential, but it's just a name for now. And then we can write down the following Lagrangian. So our Lagrangian is given by a kinetic part plus the interaction part. The kinetic part is the same thing that we wrote before. There is d mu phi I star d mu phi I plus psi I dagger I sigma bar mu d mu psi I plus fi squared. And the interacting part is going to be equal to the following thing. There is dw over d phi I times fi minus 1/2 d squared w over d phi I d phi j psi I t epsilon psi j plus the Hermitian conjugate. And that's it. So if we write this Lagrangian, we can check, and that's another exercise that I want you guys to do, is you can check that this L is supersymmetric. And actually the only thing that you need to check here is the interacting part, because this guy is obviously supersymmetric, just like we saw before. And you can already see what's happening. You take the SUSY transformation of this. So you need to, first of all, take the SUSY transformation of this part. You'll get the second derivative of W. And then you'll get another part from F. And when you substitute these transformations, you'll find that the Lagrangian is supersymmetric. Now, I don't even need to go through all this song and dance. As we'll see very soon, when we go to superspace, we'll know automatically that this thing is supersymmetric. But basically, you can show that any Lagrangian of this type with these SUSY transformations is supersymmetric. So there was a question? Yes?
Why do you put the F in the kinetic term, the F squared?
Because that's going to be there independently of W. So the superpotential W is the thing that dictates the interactions. But this is sort of the kinetic term in quotes for F. Okay? It just means that if I didn't have this part, if I didn't have a superpotential, I impose the equations of motion for F, which just means that F is 0. There's nothing. In the presence of interactions, F will be given by essentially the derivative of the superpotential. Yes?
So the field F is added to the algebra goes on check. What's the importance of this?
So you can, first of all, it's nice that you don't have to actually impose the equations of motion, that you just have something simple that holds independently of that. But as you'll see, the real utility is essentially what we're starting to see now, the ability to write Lagrangians that are manifestly supersymmetric. So that's the first step. There was another question? Yes?
About superpotentials, so far we already know that it has to be analytic, so are there any prescriptions to construct it, or?
Not really. I mean, we'll see some examples. But it really just means that it's got to be a function of the phi's and no phi daggers. Sometimes instead of saying that it's an analytic function, we say that it's holomorphic. It really means the same thing. And we're going to see some examples of that. Okay, so now with this bit of formalism, we can really derive all the previous results that we have. So let's see how all the results that we had previously come up in this language. So the first thing to note is just the thing that I started to say now. If I impose the EOM for Fi, I find that Fi star is given by minus dw over d phi I. And then when you impose that, when you stick that back, when you substitute that back into the Lagrangian, you will see that the scalar part, namely the scalar potential, is just given by sum over I fi squared. So we see automatically that v phi is always above 0. And we can also see that v phi is 0 if we have a supersymmetric theory. Or let me put it the other way, v phi at the minimum is non-zero if and only if supersymmetry is broken. So how do I see that? In order to get a non-zero v at the minimum, I need one of these f's to be non-zero. And looking over here, you'll see that f appears over here. So you think about, so these are the supersymmetry transformations, right? So the question is, which one of these guys can get an expectation value? Which one of these guys, if I take delta, so let me start from this one. If I look at delta xi psi in the ground state, this guy can get an expectation value because this is a fermion, so the transformation of a fermion is a scalar. And indeed, you see that this happens if f is non-zero. So there's some field transformation that is non-zero in the ground state. And that means supersymmetry is broken. If you think about it a little bit, you'll convince yourself that no other term here can get an expectation value because it would just break Lorentz. So supersymmetry is broken only if our potential is non-zero at the minimum. So that was the first result that we saw. The other thing that we see is we can write down all the examples that we had before. We can write them down very simply using this language. So the first example that we had was this example with the phi plus, phi minus, psi plus, psi minus, and we wrote down the Lagrangian for that. And you can convince yourself that for this case, the superpotential was just m phi plus, phi minus. So what you should do with this is just take this superpotential, use the prescription that we gave, and derive the Lagrangian. And you'll see that you get the Lagrangian that we wrote before. But now you see that it's a very simple superpotential. It's just a mass term connecting phi plus and phi minus. And it looks just like the mass term for the fermion. For the fermion, I had to have, I need to combine two psi lifts, two left-handed psis, and it's necessarily the psi plus and psi minus. So now, at the level of the superpotential, the whole field behaves in roughly the same way. If I think of this as the scalar, then the mass term for the scalar is very similar to the mass term for the fermion. So this is the sense in which I said that supersymmetry makes a fermion makes a scalar behave like a fermion. So the structure of the mass term, the structure of the mass that I'm allowed to write is very similar to the fermion mass term. Then we had the second example where we added this h to the story. So we added h and h tilde. What's the superpotential in this case? In this case, the superpotential is h phi plus phi minus. And again, you can take this superpotential and derive the Lagrangian, and you'll find the Lagrangian that we wrote down before. And once you work out this Lagrangian, you see that the interaction is completely dictated. The interaction comes from here, and if you write down the Lagrangian, derive the vertices, you will see that starting from this sort of interaction with H, psi plus and psi minus, we necessarily generate all the other interactions that we already mentioned, like phi plus H tilde, psi minus, and so on and so forth. So the structure of the interactions is completely dictated by supersymmetry. There's no freedom in that. Then we had another example that we showed, which was an example of a supersymmetry breaking theory, the Rafferty model. So let me show you the Lagrangian for that. So for the Rafferty model, the superpotential is of the following form: phi 1 squared minus f plus m phi 1 phi 2. And again, you can take this, derive the Lagrangian from this, and you'll convince yourself that you'll get the, in particular, the potential that we wrote down before. So the potential that follows from this is the following. So I already said that we need to take each f term and square it, and each one of the f terms is given by the derivative of the superpotential with respect to the field. So starting with phi, for example, I need to take the derivative with respect to phi, so I'm going to get phi 1 squared minus f absolute value squared. Then for phi 2, I'm going to get m squared phi 1 squared. And finally for phi 1, I'm going to get 2 phi 1 minus f, 2 phi 1 plus m phi 2, and the whole thing squared. So that also corrects the typo that I had last time. You see phi does appear here. And so now you can take this Lagrangian and you can verify that we have the spectrum that I said we have. So we can now derive the spectrum for the scalars and fermions. So all the examples that we wrote down are very simple superpotentials, and you can derive the Lagrangians from them. Any questions before we go on? Okay. Okay. So the next thing that we want to introduce is superspace. But before we introduce superspace, we want to introduce some notation. So let's do that. And it's really just intended to simplify the way that we write spinor bilinears. Okay, so we want to introduce some spinor notation. So let me remind you how we started to write our spinors. We said that a Dirac spinor can be written as a psi L and psi R. So I'm going to take the psi L and label it with indices alpha, with alpha going over 1 and 2. The bilinears that we had before were of the form psi chi t, for example, epsilon psi L, and this epsilon was a matrix 0, -1, 0, 1. So I can now define epsilon 1, 2 equals minus epsilon 2, 1 equals -1, and epsilon 1, 1 equals epsilon 2, 2 equals 0. And then instead of writing this guy, we can just write epsilon alpha beta, psi alpha, psi beta. Yes? That's right. Oh, I'm sorry. Thank you. Okay, so we can write it in this way, and then we can use the epsilons to raise and lower indices. So this thing I can define to be psi alpha, psi beta. Okay, and my chi's and psi's change too. So let me take care of that. So this was supposed to be chi alpha, and this was supposed to be chi alpha and psi alpha. And we can also define epsilon alpha beta to be minus epsilon with the upper indices. And that defines for us psi L alpha as epsilon alpha beta, psi L beta. Now you can easily check that epsilon alpha beta, sorry, let me do it this way, epsilon alpha beta, epsilon beta gamma equals delta alpha gamma. And you can also check that psi chi is equal to chi psi. So this was all for left-handed spinners. Now let's talk about the right-handed spinners. So the right-handed spinners we want to label by dotted indices. So for these guys we're going to use dotted indices which also take the values 1 and 2. And then there are a bunch of things to notice. First of all, the gamma matrices. So the gamma matrices I can write as 0, sigma mu, sigma bar mu, 0 in block diagonal form. So these guys are sigma mu alpha, alpha dot. And these guys are sigma bar mu alpha dot alpha. And we said already that I can always write a right-handed spinner as a left-handed spinner with an epsilon and complex conjugation. So I can decide to work with either with left-handed or with right-handed spinners. And so we need to decide on some convention, how we're going to associate indices. And so the convention is going to be the following, and that's just a convention. The left-handed guys we're going to write with no daggers, and the right-handed guys we're going to write with daggers. And so now let me explain what we really mean. Okay, so for a left-handed spinner psi x, I'm going to write it as psi x with an alpha. For a right-handed spinner psi x, I'm going to write it as chi dagger with an index alpha dot for some pi. So this is the way left-handed spinners are going to be written. This is the way right-handed spinners are going to be written. And so the only thing I need to tell you now is, just like we had spinor bilinears here, I can construct spinor bilinears with dotted indices. So the way we're gonna contract these is the opposite way. So this thing is defined to be psi dagger alpha dot, psi dagger alpha dot. So the contraction in this case goes like here. Alpha, first there's the upper index, then there's the lower index, and here it's the other way around. Okay, so that's all a lot of notation. Oh, and one more little notation, as if this is not confusing enough. Sometimes we, instead of writing a dagger, we write a chi bar. So you'll see different people use different notations, but this is very often done. Instead of writing a dagger, you can write a bar. And I think that's the end of the boring part. Yes. Okay, any questions about this indexology? Okay. Yes.
Is this just the helicity basis for the pronouns?
Excuse me?
Is this just the helicity basis for the pronouns?
It depends on what you call the helicity basis. So it's just two-component notation with dotted and undotted indices. Okay. Okay. So now we're finally ready to really move forward and introduce superspace. So I feel like a complete alien here with all these little things like me teeth. So it's appropriate to move into outer space. So we're gonna talk about superspace now. Okay, so what's the idea? What's the basic idea about superspace? So we said that supersymmetry is an extension of space-time symmetry. Space-time has to do with x mu. So it seems fitting that we should add to that, once we have supersymmetry, we should add to x mu some more coordinates. These coordinates need to be anti-commuting coordinates because the SUSY transformations are anti-commuting, they're Grassmannian things. So we add to that also theta alpha and theta bar alpha dot. So we add two sort of new coordinates, which are Grassmannian coordinates. And alpha dot take the values 1 and 2. Now, if we have a space-time transformation, then the space-time transformation takes the x mu into some x prime mu, where the different components of x mix between themselves. So exactly the same thing should happen for supersymmetry transformations. For a SUSY transformation, we should have x mu, theta, and theta bar go into some x, drop the x mu here, into x tag, theta, and theta bar prime, where these guys are some mixtures of these guys, just like for the normal coordinates. Yes?
So this is the superspace for n plus 1, right?
Yes.
If we're doing it right, we have more.
Exactly, right. But I'm just going to talk about n equals 1. Okay. So let's continue the analogy one more step. So if I'm talking about space-time transformations, let me put it over there. If I'm talking about space-time transformations, then I have If I'm talking about something that's not a scalar field, like a vector field, for example, what happens is that this guy transforms into an A prime, where these components are some combinations of these components. The components mix among themselves. Similarly for psi alpha, it goes to a psi alpha prime, where these guys mix among themselves. So it's going to be exactly the same thing for superspace. Once we go to superspace, we have to talk about superfields, which are functions of x, theta, and theta bar. These are going to have different components, and under some supersymmetry transformation, the different components are going to mix among themselves. So that's what we're going to see. Okay, so let me write down a general superfield. It's something that will depend on x, theta, and theta bar. And of course, these guys are very weird coordinates, so I need to make sense of this thing. So what does this thing mean? It just means that I can formally expand this function as a Taylor series in theta and theta bar. And the components and the coefficients of that are going to be normal fields. And because theta and theta bar are Grassmannian, this is going to be a very short expansion. Okay? Because theta, we know that theta 1 squared is 0, and similarly for theta 2. So the only things that we can write down are things that have no thetas, or a single theta, or theta 1, theta 2, which I'm going to call theta squared, up to a factor of 1/2. Okay? So we can just expand this field. And so the general superfield is a very simple form. So A of x, theta, and theta bar is equal to, first of all, something with no thetas, then some theta alpha with a coefficient that I'm going to call B alpha for now, and then theta bar alpha dot C alpha dot of x plus theta squared D of x plus theta bar sigma mu theta E mu of x, and so on and so forth. And the very last thing that you can write is theta squared, theta bar squared, times something that I can call, I don't know what, let's call it g of x.
Did you say that the expression is 0?
That what?
That expression is 0?
Because the theta squared stands for theta 1, theta 2. I have two thetas. Theta is a spinner, so it has a theta 1 and a theta 2.
But this, what means this one, the 0?
So theta squared, by definition, I don't know if you can see this.
The other equation.
Oh, theta 1 squared. Theta 1 is 0. But theta 1, theta 2 is not 0. But that's all I can write down. So you see that you get exactly what you expect. I mean, we just Taylor expanded this thing in theta, and we get something that carries no Lorentz index. So this is a scalar from the Lorentz point of view. This guy is a left-handed fermion, a left-handed fermion. This guy is a right-handed fermion. This guy over here is a vector. And so in the same superfield, we have fields that carry different spins, which is exactly what you'd expect, because a supersymmetry transformation takes one spin to another. So in the same superfield in the same supermultiplet, we should have things that have different spins, and they should transform into each other under the SUSY transformation. Is that clear? Okay, I don't know if it's too early or it's too bad. But hopefully it will become, if it's not clear, then it will become clear as we go along. Okay, so we should see how under a SUSY transformation these guys get mixed between themselves. So let's see this specifically. So under a SUSY transformation, this A of x theta bar should go into A of x theta bar plus some shift. And now we can write down what this shift is. So delta xi of A of x theta bar will be given by xi q plus xi bar q bar A x theta bar. And let me write down what q is, and the same thing is gonna hold for q bar. So q alpha is given by d over d theta alpha minus I sigma mu alpha dot theta bar alpha dot d mu, and similarly q bar alpha dot is given by d over d theta bar alpha dot minus I theta alpha sigma mu alpha beta dot epsilon alpha dot beta dot d mu. Okay, so I define here q alpha and q bar alpha dot, and basically this tells you how the superfield transforms under a supersymmetry transformation. So this guy xi is just the SUSY transformation, the parameter of the SUSY transformation, which is a spinner, and we dot it with a q, and this is the transformation of the full superfield. Now this looks very weird until you actually perform the transformation. So if I do this for a superfield that I already know, I should recover everything we said about how the different fields transform. So indeed, that's exactly what happens. And we can see that in stages. So the first thing that I want you to check, and again, this is another exercise, I want you to show that A prime of x theta and theta bar, namely this guy over here, is equal to A of x mu minus I sigma mu theta bar plus I, sorry, where's my xi? So this should be I xi sigma mu theta bar plus I theta sigma mu psi bar, and then theta plus xi and theta bar plus xi bar. So this is an exercise. How would you go about doing that? So the first thing you can do is you can just take this take this transformation and apply it on this field as it's written here. The other thing that you can do is you can start with this equation and take this guy and just Taylor expand. So again, I can Taylor expand this in theta and theta bar, and I'll get some very long expression here, and I can compare that with the result of doing this over here. And you don't need to do that for, you know, all the fields, of course, all the components, just one or two, so that you can convince yourself that this is really what's happening. So you see that this is exactly what you'd expect. We do a supersymmetry transformation. It means some transformation that involves the x's and the thetas, and they mix in this way. So this is very natural, and this is also natural once you consider that these are really the only options that can come in. So, which one? In the definition of A, oh, this guy here. Yeah, thank you. Yes. What is?
Is it this generator responsible for this transformation for the first one, right?
Yeah. Mm-hmm.
This two.
Right.
Just show how you actually have to use this Q and this X.
Oh, so the Q, so I can do the following thing. So
These two ones, I understand how you use this to Q alpha, but then the question is what kind of generators you use to do this transformation.
oh, I didn't use that. That was the only generators that I used. But in order to show this, okay, so here's what I should do in order to check this. Okay, first of all, I can, so here's my original A. That's my expression for A. Okay, now I can take the same expression, but substitute, instead of x mu, substitute this thing here, and Taylor expand. So for each one of the fields, for example, I can take the first thing that I had over there was just the scalar A of x. Now I have A of x minus IXC sigma theta bar plus I theta sigma xi bar.
I was confusing even myself, so I understand how to do this, but for me it is important what kind of generators are responsible for this. It is this Q alpha and Q alpha dot, right?
Right. Yeah. Okay. Good. Okay, any more questions before we go on?
And field, is this not current, or this field that we used before?
These are, okay, so you're asking what's the relation between these Qs and the Qs that we introduced before, the SUSY generators. These are precisely the SUSY generators, but now I wrote down an explicit form for these generators. Right. Okay. So one place where we can really check this is going back to the super multiplet that we had before. So before we talked about the chiral super multiplet. The chiral super multiplet is just one special example of a superfield. It's a superfield that's called the chiral superfield. So I'm going to use S field for superfield very often. And let's write it down. So what's the chiral superfield? Phi x. It has phi x plus square root of 2 theta psi x plus, let me continue over here, I theta sigma mu theta bar d mu phi x minus I square root of 2 theta squared theta bar sigma bar mu d mu psi x plus theta squared f of x, and finally 1/4 theta squared theta bar squared box phi x. So it's very long, but it contains just the fields that we had before. It contains phi, the scalar field, the fermion psi x, which is just the left-handed fermion. You see there's no daggers on it, and it comes with a theta, and f. So it's exactly the fields that we said that we have before, phi, psi, and f, and they appear in different combinations here. So you see both psi and the derivative of psi over here, and so on and so forth. So now, for this guy, we know exactly what the SUSY transformations of these guys were, so this is something that we can check. We can really try to see whether we get the SUSY transformations that we already know. Okay, so let's do this. So now we want to take delta xi and act on this phi guy. So the thing that let's start with this term here. So I want to take, first of all, xi times q and apply it on phi. So there are two parts here. So there is the xi, and then there is d over theta alpha minus the rest, which I'm not going to write down here, and I want to apply it on phi. So let's first of all look at the d over d theta piece. And let's say that the thing that I want to do here is I want to see from this delta, from this transformation, I should get delta xi of the scalar field, delta xi of the fermion field, and delta xi of f. So let me for now do the first one. Just look at the SUSY transformation of the scalar. So what am I supposed to do? Phi is going to go to some phi prime, and the scalar field is just the first component, the lowest component in the expansion. It's the thing that appears with no thetas. So in order to look for the transformation of this guy, I should apply this thing. I should look at, for example, xi alpha d over d theta alpha of phi, and keep just the term with theta equals 0 and theta bar equals 0. Because I'm looking for the lowest component. I'm just looking at the scalar field. So let's see what we get. So we take this guy, and we take a derivative with respect to theta, but we should keep just the stuff that doesn't have any more thetas. So this doesn't give me anything, because there's no thetas. This will give me, when I take the derivative with respect to theta, I'm going to get square root of 2 times psi. So that's the first thing that I get. Delta phi is square root of 2. And then I, of course, have the psi alpha, so let me put the psi alpha outside. So I have square root of 2 psi alpha And there's nothing else that will contribute. Because here, I'm going to get rid of this theta, but then there's another theta bar that stays over. So when I take just the no theta piece, there's nothing that's going to contribute, and similarly for all of these guys. So this is the only contribution that comes from the d over d theta. Then there's also this piece. So now I should look at the contribution coming from this part of the q. So I should now take a derivative with respect to x and multiply with a theta bar and keep the stuff that doesn't have any thetas. So you'll see that the only thing that will, you'll see that there's nothing that will contribute here because there's always going to be a theta bar here. So this is really the only thing that we have. Okay? So if you go back and look at the transformations that we wrote down, this was exactly the transformation that we wrote down for the scalar field. So you can repeat this for the whole thing and convince yourself that that's really true. Now, another thing that you can check is that there's the piece with a q bar. So the piece with a q bar doesn't give anything. So q bar acting on phi gives nothing. And that's a special property of the chiral superfield. Okay, questions about this? Okay, so this is a lot of algebra, but it's fairly simple algebra. Okay. So a few comments about this story. And let's see what I can get rid of. Let's get rid of this. So first of all, just in order to keep track of dimensions, it's useful to look at the dimension of theta. So in this expansion here, for example, we have a scalar field, which is dimension 1, and then psi, which is dimension 3/2. So the dimension of theta is minus 1/2. Another thing that we can notice is that f is the highest component field. It's the coefficient of theta squared. So you'll see that if I look at things that don't have any derivatives in them, phi x multiplies no thetas, psi multiplies a single theta, and f multiplies 2 thetas. It's the coefficient of theta squared. So I can write it as in the following way. I can say that f of x is the theta squared component of phi x. And what you should recall is that the SUSY transformation of f of x was a total derivative. So if I write down a Lagrangian that contains f of x, it's going to be supersymmetric by definition, because its transformation, its SUSY transformation, is a total derivative, and so it's automatically supersymmetric. So that's a very important result, because it tells us the following thing, but we need to know one more thing before we get the result. So I'm not going to show this, it involves more algebra. Some of it is straightforward and some of this is not, but you can convince yourself of the following thing. If you have phi 1 and phi 2, which are chiral superfields, then phi 1 plus phi 2 and phi 1, phi 2, and actually any polynomial that you can write down, any function of phi 1 and phi 2, is also a chiral superfield. So any function of this type, if we write it down in components, its highest component is going to be something that we call some f, and the SUSY transformation of that f is a total derivative. So remember that before we had the superpotential W phi I, which we defined to be just a function of the phis, not the phi daggers. Okay? So this guy, because it contains all sorts of combinations of chiral superfields, it's also a chiral superfield. And therefore, if I put in the Lagrangian, if I include in the Lagrangian a term of the form if I include the theta squared component of this chiral superfield, I'm going to get something that's supersymmetric. So before I thought about the superpotential in terms of the scalar fields, because we didn't have superfields yet. Now I want to promote this guy to be a function of the chiral superfield. Then I know it's a chiral superfield itself, and therefore if I take its theta squared component, I can put it in the Lagrangian and it's going to be supersymmetric. So usually the way we write this, instead of taking the theta squared component, we say that we have a term in the Lagrangian that we can write as d squared theta W of phi I. And remember, because we're talking about Grassmannian variables, taking the theta squared component is exactly the same as doing the d squared theta integral. Because what we need to remember for Grassmann variables is that d eta a plus b eta is equal to b, where eta is Grassmannian. And in this case, we have two Grassmannian variables. We have d theta 1, d theta 2. Okay, so taking the d squared theta integral is just taking the theta squared component. Okay, so at this point, we know how to construct interacting Lagrangians if we only have chiral superfields. If we just have chiral superfields, the L interaction necessarily comes from some W that involves the chiral fields, and we take the theta squared part of W, and that's precisely, and this precisely justifies the recipe that we gave before, because we know that this component will give us a total derivative. So taking this piece in L just means that under a SUSY transformation of L, we get a total derivative of something. And if you look back at the recipe that we gave, and you look at the interacting Lagrangian that we gave, it's precisely the right thing. So we wrote down something like dw over d phi I times fi plus other stuff. And if you work out the theta squared component of the superpotential, that's exactly what you'll get. There was a question somewhere? Yes? Why do we always? Because for the chiral superfield, we said that the theta squared component, the coefficient of the theta squared is the thing that transforms as a total derivative.
How do we ensure that do we do some constraints on how f should look like, or is
No, it just follows from, if you just work out the transformations that we had before for the chiral superfield, you'll see that the thing that was multiplying theta squared, call it f, this guy necessarily transforms as a total derivative. But you have to use the transformation that we wrote. That's a good exercise to do. More questions? Okay. Okay, so far we know what to do about chiral superfields, but of course if we want to do anything useful with this, we need to know what to do about gauge fields. So let's talk about that. So now we want to introduce gauge fields. And the superfield, remember, the chiral superfield was something that had a complex scalar and a fermion and other things, but it had a complex scalar. For a vector field, we need something that's real, because a vector field is real. So we need to introduce another sort of superfield, which is the real superfield. So the real superfield is a superfield V that satisfies that V dagger equals V, very simply. So now you can write down what this thing can be. So again, it's something that depends on x theta theta bar, and it's of the following form: C of x plus I theta chi of x minus I theta bar chi bar of x plus, let me put this guy in parentheses, theta squared m of x plus I n of x plus the complex conjugate minus theta sigma mu theta bar v mu of x plus I theta squared theta bar lambda bar of x plus 1 plus I over 2 sigma bar mu d mu chi of x plus the complex conjugate, and finally we have 1/2 theta squared theta bar squared d of x plus 1/2 box c of x. And there are all sorts of conditions on these fields, right? From the fact that V dagger equals V. So this is a real scalar, this is a real fermion that is a Majorana fermion, this D is also real, and so on and so forth. And in particular, V mu is real. But now what I'm really interested in gauge fields. So for a massless gauge field, I know I should just have 2 degrees of freedom. And I know exactly what it does under a gauge transformation. So under a gauge transformation, V mu goes into V mu of x plus d mu lambda of x, where lambda is some function. This is just a gauge transformation. But now we want to write down something that's supersymmetric. So if I want to make this supersymmetric, I better promote this guy to be a superfield, because I want the gauge field. So I start with something and then do a gauge transformation, and then I should still get something that's a legitimate component of the superfield after I do the gauge transformation. And notice this lambda is not a constant, it's something that depends on x. So something is going to happen to it under a supersymmetry transformation. So what we need to do now with SUSY is we need to take the full superfield V to V plus I lambda minus lambda dagger, where lambda is a chiral superfield. Now, let's look at what is, so again, what did I do here? I just used the fact that this guy has to become a superfield, and I want something that's real, so I have to take this combination of lambdas. Now, if lambda, I already know what the chiral superfield looks like, so I can write down what this thing is. So, this thing here, I lambda minus lambda dagger, is equal to minus 2, the imaginary part of lambda, just the scalar part, and then plus 2I times theta psi minus complex conjugate plus 2 theta sigma mu theta bar real lambda plus some other stuff that I don't want to write down. So you can see what happens. V transforms into this thing. Now I get this new piece. I'm mainly interested in the V mu. The V mu was sitting over here. The V mu is the thing that multiplies theta sigma mu theta bar. So under the transformation, it's going to shift by something that's proportional to real lambda. So that's exactly what we need. I mean, that's the usual gauge transformation. But there's other stuff that's happening too. In particular, I get this imaginary lambda. So the imaginary lambda I can choose such that I get rid of the C of x. I can just choose the imaginary lambda to get rid of this guy. Similarly, I can choose this psi here to be equal to minus this guy here and get rid of this guy. So what are we doing here? We're really doing not a gauge transformation, but a supersymmetric gauge transformation. And this allows us to get rid of some of the unphysical things in the vector superfield. So essentially, we can get rid of lots of stuff this way, except for the following things which will stay. The things that will stay are, first of all, this guy, and also this lambda here, and the D here. Everything else is stuff that we can get rid of. So after doing this gauge transformation, what we're left with is just V mu, lambda, and D. So what are these things in standard language? This is the gauge boson. This is the gaugino. It's a real fermion, it's a Majorana fermion. And this guy, just like we had before, is an auxiliary field. And you'll notice that the auxiliary field, D, is the thing that multiplies the theta squared, theta bar squared part of the superfield. So that's again a highest component field. It's the highest component field, and it's an auxiliary field, just like we had for the chiral superfield. So doing this super gauge transformation, we eliminated a lot of the unphysical stuff from the superfield, and if we just keep these guys and get rid of everything else here, this is called West-Zumino gauge. So working in West-Zumino gauge just means that you keep these physical things in V, which you cannot get rid of. Okay, how much time do we have left? Okay, any questions about this before we go on? Yes.
The trees are from gauge transformation V to V plus I
But it's a superfield, right? So lambda is a chiral superfield. So I can write it down as, first of all, let me call it big lambda, and then I have lambda x, which is just a scalar, and then I have well, let me not write all the factors, but I have something which looks like theta times psi, and the whole zoo that comes after that. Okay? More questions? And sometimes I'm not distinguishing between the superfield and the first component field, especially for the chiral superfield. Sometimes I call lambda and its lowest component the scalar, using the same notation. But that's a little confusing, but you get used to that. Okay, more questions? Okay, very good. So, at the end of the day, we see something that looks right. Looks like we're doing the right thing. Because if you think about a massless vector field, the massless vector v mu has two physical polarizations, so 2 degrees of freedom. And what we find is that it's coming with a Majorana spinner that's also 2 degrees of freedom. And then there is an auxiliary field, so we don't care about it because it's not dynamical. So in terms of physical fields, we have the same number of fermion and boson degrees of freedom, just like we said we should. So that's good. And another thing that we notice is we said that the highest component is the auxiliary field D. And it's actually multiplying theta bar squared. It's really the highest component. And therefore we know that if we write down a piece in the Lagrangian that goes like D for theta times a real field, which is the same thing as saying that we take a real superfield, take its theta bar squared component, and write that as a term in the Lagrangian, that thing is going to be supersymmetric. We don't need to check anything anymore because we took the highest component of the field, and therefore we know that its SUSY transformation is a total derivative. So everything should work. So now we can complete the story that we had before and write down the full Lagrangian. So we go back to chiral superfield example, and there we said that the Lagrangian had two parts. It had the kinetic part, and then it had the interaction part. But the interaction part we could write down as d squared theta times w, which depends on the chiral superfield. But this part we just wrote down in components. Now we know how to write this guy too, because obviously phi dagger phi is real. So if I start with a chiral field phi dagger phi is going to be a real superfield. And so I know that d for theta phi dagger phi is supersymmetric. And in general, if I do things a little more generally, I can take a real function of phi and phi dagger, which I'm going to call k of phi and phi dagger. This guy is usually called the Kähler potential. But the only thing that matters for now is that it's a real function of the phi and phi dagger. And then I know that d4 theta of k phi and phi dagger is supersymmetric. And actually, you can convince yourself that if we take k of phi dagger to be just phi dagger, then our kinetic term is equal to d4 theta phi dagger. So now we know how to write down the full Lagrangian for chiral superfields in terms of superspace machinery. And this simple form, this phi dagger phi, is just what's called the canonical Kähler potential. So the canonical Kähler potential is just phi dagger phi. And that's the thing that would give you the canonical kinetic term for all the fields. In principle, you can have more complicated things that include corrections to the canonical kinetic terms and wave function renormalizations and things of that sort. But the important thing is that the kinetic part is coming from the real combination of phi and phi dagger. So it's better to put the dagger over here. Okay, questions about this? Okay, so I think we should really stop here, and it's not a bad place to stop. So basically, we know everything we need to know about chiral superfields. We have a little bit of stuff to add about writing down the kinetic term for the gauge field, and then we can write down both the supersymmetric standard model and all the other theories that we'll be interested in. So I'm gonna stop here. But basically, my consolation to you is that this was the hard stuff. I mean, now we got through all the formalism, we understand it very well, and now we can just apply it very simply. That's assuming that you sit today and go through all these horrible transformations, but once you do that, it's very clear. Okay, thank you. More questions? Yes?
Just the regards term, when you derive a canonical kinetic term, is it an error that daggers in the wrong phi, or is it just a convex conjugate?
Oh, it's just, so first of all, I should really put the daggers over here. So this is, phi is the chiral superfield, so it has all the stuff that we wrote down. There's the scalar, and then there's theta times psi, and so on and so forth. So now I'm just really taking the complex conjugate of that.
So it's really large, capital phi form.
Yeah. Mm-hmm. Yes?
I wonder how should I count the degree of freedom of vector subfield in the of the material, especially in the other in general dimension like 2D or.
Oh, you're asking, I'm sorry, the acoustics is really bad here.
Yeah, how should I count the degree of freedom
The vector field,
Yeah.
how should I write down its, how should I count its degrees of freedom?
Yeah. Of the mesh shadow.
Oh, okay. So we can also do that. So off shell, so there are two things here. So first of all, if we go off shell, we really have to include the full stuff that we wrote over there, and then we just have to really count it. But then when you do that, it works out. I don't want to do that because there's a lot of garbage there. Yeah. There was something else? Yes. Maximal number?
Yeah.
So we are asking what is the analog of the superpotential for if I have maximal supersymmetry?
No, the maximal number of superfields that you can have inside the superpotential. I know that it is 3.
Oh, okay. So you're asking in the superpotential, how many fields can I have? No, I can have any number of fields. We'll see examples with lots and lots of fields that show up. And just like when you talk about Lagrangians, you can write down terms that have dimension 4, and you can write down non-renormalizable terms that involve higher power of the fields, but are down by some scale to some power. Then it's exactly the same thing here. I mean, I can, in principle, write down here something like phi cubed. I can write down a mass term, which is something that we already saw, which roughly speaking is phi squared. But I can also write down phi to the 17 if I have lambda to the 14 here. So you'll notice that the dimension of the superpotential is 3. And the way to see that is that in the Lagrangian we have d squared theta w, and we said that this guy is basically dimension 1, and so this has to be dimension 3. More questions? Yes?
Are there any conditions on the K?
Basically any real function, roughly speaking.
And how do you make sure that if it's not a polynomial function, for example, all the superfields will remain superfields?
Okay, that's a good question. We're going to come back to that when we talk about some non-perturbative stuff. I mean, there are some constraints on the general Kähler. It basically has to be associated with some Kähler manifold. There has to be a metric that I can construct out of this. So the metric is going to be given by d squared k, this second derivative. This is something that needs to be invertible and so on and so forth. It needs to describe a good metric of some sort of manifold. But for starters, the canonical Kähler potentials that we're going to write down are just phi dagger phi. And then you can think of all sorts of corrections. The easiest corrections that you're going to encounter in perturbation theory are just some wave function renormalizations. So, I mean, this can receive some delta z phi dagger phi. So overall, I can write this thing as z phi phi dagger phi, where this depends on the scale where I'm calculating. It includes all the RGE, everything that I get after doing the RGEs. But in principle, I can have much weirder functions show up here. So once we include non-perturbative stuff and look at strong coupling, you can have all sorts of weird Kähler potentials. The question is, what you do want them to do in order to have, you really want to know that you're starting with the canonical kinetic term. Otherwise, things don't make sense, right? So if you have something that become singular instead of behaving as phi dagger phi, then something's wrong with your theory. Okay, so we finish now.